జాయిన్ ఉంటుందా ముగ్గురు ఓకే So today we'll see this what we call two electron system, that is the Landau G factor in LS coupling and as well as the Landau G factor in JJ coupling and Zeeman effect for two electron system. Okay, these three topics we'll see here. That is unit 11. Okay, unit 11 which we have. So first we'll move to this one. So are you able to see now this screen? Right. So first we'll take this Landau G factor in LS coupling. Landau G factor in LS coupling. Okay. లేకపోతే so now we'll see this Landau G factor in LS coupling. So this Landau G factor in LS coupling, it is a quantity that describes the relationship between the what we call angular momentum of an atom and its magnetic moment. Okay. So Landau G factor in LS coupling, what it is going to be describes means it is a quantity that describes the what we call relation. It gives the relation between the angular momentum of an atom and its magnetic moment. Momentum in the presence of what we call a magnetic field. In the presence of magnetic field. Right. So mainly this Landau G factor in LS coupling, what it is going to give means it is a quantity that describes the relationship between the angular momentum of an atom and its magnetic momentum in the presence of magnetic field. Okay. In the presence of magnetic field, it is going to be give the relationship, quantity, it is going to be give the moment between the relationship between the angular momentum of an atom and its magnetic momentum. That is what we have to see here. Okay. So now first we'll see, we'll consider a two electron system in an atom. Okay, 1 minute. So first what we'll do is we will take a two electron system in an atom we are going to be considered. So we'll consider two electron system in an atom. Right. So as we take the two electron system in an atom, so there will be four individual magnetic moments to be taken into account, which are associated with this what we call mechanical moments. So what are those we are going to be have is here we'll take like S1 star, okay, S2 star, comma, L1 star, and L2 star. You know that what are those S1 star, S2 star, and L1, L2 star means due to the orbital motion, orbital magnetic movement, due to two electrons, you are going to get it as a L1 and L2. And similarly, we have a spin motion of the electron. Due to that, we will be having what we call S1 and S2. You are going to be have like this four what we call magnetic mechanical movements will be there here. So now with the magnitude of each movements, the vector sum will be depend on their what we call mutual orientation. So we know that LS coupling is nothing but what? Okay, LS coupling is nothing but it will in between this orbital angular momentum and spin momentum you are going to be have, right? So here we will take the magnetic movements of the spin and orbital motion of the electron. Here we are going to be consider here. So magnetic movements we are going to be consider the both the spin as well as the orbital we have to consider here. So now first we will take this magnetic movement of the orbital motion of an electron we are going to be taken. So that we will be writing as mu L. Here we are going to be writing. Okay, mu L. So mu L is nothing but what? It is a orbital motion, magnetic movement of orbital motion of an electron, which we are going to be call it as a mu L. So which is given by what? L star we have and H by 2 pi into E by 2m. So this is already we have seen this one. Okay. Magnetic momentum already we have seen. So that is given by mu L is equals to L star into H by 2 pi E by 2 mc you are going to be have. Similarly, as the electron is revolving on its own axis in a magnetic field, so due to that, it is going to be have what we call magnetic movement of spin of an electron you are going to be have. That is given by what? Mu S. It is given by. Is given by what? Mu S. So mu S is equal to, we are writing it as 2s star into H by 2 pi into E by 2 mc you have. E by 2 mc. So these are orbital and spin magnetic movement of an electron. Mu L is orbital magnetic movement of electron and mu S is nothing but magnetic movement of the spin orientation which we have. So, and we know that in the case of the LS coupling, so we have to add these two. That is the magnetic moment of this, both we have to add. Otherwise, in LS coupling, the two spins are coupled strongly. Okay, the two spins are coupled strongly here. So that what we are going to take means we are going to be take like for spin, both S1 and S2, we are going to be considered, and for what we call orbital momentum, we are going to be considered both L1 and L2. So therefore, we are going to be write the vector sum of the two magnetic moments. Vector sum of the two magnetic moments we are going to be write. So first we will write this mu S. This mu S we are going to be write. So this mu S is equal to, we are writing it as what? S1 star. Okay. S1 star into cos of S1 star and S, capital S this one. Okay. And similarly, for the second one, S2 star cos S2 star capital S star into H by 2 pi into, we have 2 into E by 2 mc. Okay. That is due to the spin. So this entire bracket, whatever we have, like S1 star cos, S1 star S star plus S2 star, that we are going to be write here at as S. Later on, we'll see that what we have. So this we are writing it as a S star into the remaining what we have is H by 2 pi into 2E by 2 mc. Right. So this one we have. Similarly, we have to write this what we call magnetic momentum of orbital motion. So that is mu L we have, right? This we are writing for two electron system. So for that one, it will be L1 star cos of L1 star L plus L2 star and cos of L2 star and L capital star. Okay. So into what we have h by 2 pi. This is common already. We have h by 2 pi into E by 2 mc. Okay. E by 2 mc we have. So this, what we'll do is, we can write it as mu L is equals to this entire thing, whichever we have in brackets, we are writing it as what? L star we are writing. And into what we have outside of this bracket, h by 2 pi into E by 2 mc we have. Okay. So one, we have got this equation. Here we have got another equation. Due to the spin, we have got one equation. Due to the orbital motion of the electron, we have got this one. Okay. So you see, whatever we have written in that one bracket, whatever we have like L1 star, L cos of L1 star into L star, all this we have written it as what? L star we have written. Okay. So here it is mentioned that the entire value we have written for spin, it is written as S star, and for what we call orbital momentum of the electron, we have written it as L star. Now we have to combine in order to get this total angular momentum, that is L plus S we have to do in order to get this J. That is a combination of this L and S are coupled together to form a resultant moment of J. Okay. So therefore, we can write we can add this what we call mu S as well as the mu L we have to add. Mu S plus mu L we have to do. So here, if you add this, we are going to get it as what? Mu J here. As we know that J is equals to L plus S. So here we'll add this mu S plus mu L is equals to mu J you are going to be have. So therefore, mu J, what we are going to get here? Mu J is equals to, it is a combination of both L and S. So L star cos of, one is L star and J star. Similarly for a spin, so it will be 2 times S star you are going to be have, and the cos of S star and J star we have, right? Into H by 2 pi into E by 2 mc you have. Okay. So simply by adding these two, we are going to get this one. So now this term, what we call EH by 2 pi, 4 pi mc outside is there, no? So if you add this one, what you are going to get, we can get it as what? The term we can write it as what? EH by 4 pi mc we can write. Okay. So which is known as what? Actually, it is a Bohr magneton. Already we have seen that it is a Bohr magneton. So the terms within the brackets here, this is going to be give what we call mu j in the units of, means this value, it is going to be give in the units of Bohr magneton. That is nothing but EH by 4 pi mc times this you are going to be get here. Okay. So now what we'll do is we'll replace these terms with what we call G and J. The terms within the brackets, what we call, we have like a mu J in the units of Bohr magneton, that is EH by 4 pi mc. Already we have that one. Now what we'll do is we'll replacing the terms in the brackets by G times J we are going to be replaced. So mu J is equals to what we are writing? G times J. Okay. G times J we are replacing. Therefore, here what we have? L star cos of L star J star, and similarly for this one, you have 2S star cos of S star J star we have. So therefore, what you are going to get, if you replace that bracket with Gj, so it will be mu J is equals to what we have? Gj into this value, entire value, EH by 4 pi mc. EH by 4 pi MC we have. Okay. EH by 4 pi MC. That is nothing but mu J. We have got it as what? GJ times of EH by 4 pi MC we have got. Okay. So now here, if you see in your book, the figure whichever we have, that is a Landis G factor in JJ coupling. Okay. So it is shown that so here it is shown that you have like what we call a magnetic field is in this direction. It is represented with H here. Okay. It is represented with H. We have what we call J vector and as well as the L vector we have. Okay. Okatemo J vector. So first, what we have at the center, we have this magnetic field in the upward direction. Around that J vector, it is precising, the bigger one. So, and we have both L and S here. Okay. L and S. అది కనిపిస్తుందా మీకు? One minute. So here, so here you see, field is in this direction you have, right? In this direction you have, it is represented with H, it is represented. So you have this, what we call, this is J vector. Have is nothing but in the magnetic field, you will be having this what we call orbital motion. Due to that, you are going to get this what we call a magnetic moment of orbital motion you are going to get. And similarly, you are going to get what? Spin magnetic otherwise magnetic moment of spin motion of an electron you are going to be get. Okay. That means it is revolving around the in the orbital as well as the on its own, it is going to be revolve. So we have got what we call a mu j value. That is nothing but mu j value. How much we have got? Actually, we have got gj star into he by 4 pi mc we have got. Okay. So as we have seen in this figure, that is the angles between LSJ are fixed here. Okay. In the LS coupling. Okay. So the cosine terms, whatever we have got, like in the in this we have got no the cosine terms in the equations. In the previous equation, like Gj is equals to what we have got L cos of Lj plus 2s cos of Sj we have got, right? The cosine terms in these equations are what we call we can evaluate That means the angle with which it is rotating, we can evaluate. That is what it is given by L. Right. So it is given by L cos of Lj. It is given by what? J square plus L square minus S square by 2j వస్తుంది. Similarly, we have the spin, that is S cos of Sj, which you are going to get it as a J square plus S square minus L square by 2j you are going to get here. So these, how you are going to get this? The Landis G factor, which states the which states the quantum numbers, this L, S, and J. L, S, and J. So that Gj, it is given by what we call actually Gj, whichever we have got Landis G factor, which we have got it as what here. Actually, it is given by 1 plus J into J plus 1 plus S into S plus 1 minus L into L plus 1 divided by 2J into J plus 1. Actually, you'll get here. Okay. So this is what you are going to get. It is given that Gj is equals to what it is given? G value it is given by what? 1 plus J square, means J star square, actually it is S star square minus L square by 2J square. Okay. So we have got this, right? Gj is suppose L1 is 1 we have taken, right? L1 ఒకదాన్ని తీసుకున్నాం కదా మనము. So L1 and L2 we have taken. Actually, we said that in the LS coupling. So actually, L is nothing but what the combination of all these we have. So we have taken L1 and L2 we have taken. That small L1 and L2 we have taken, right? So for 2-electron system, the total angular momentum is given by what? L is equals to actually L1 plus L2 we have. So where this L1 and L2 are nothing but the orbital angular momentum of the individual electron. So L1 is for one electron, L2 is for another electron. So the combination of this is nothing but what? Total angular momentum of the individual electrons we have. Similarly, the spin angular momentum of the electron is given by what? Actually, S is equals to S1 plus S2. S1 plus S2 actually. So that S1 is nothing but what? Actually, it is a spins of the individual electrons. S1 is one spin of the one electron. S2 is another electron. So therefore, by combining these two, what you are going to get actually? J is equals to L plus S you are going to get. So this J is nothing but what actually? This is the total angular momentum. J is equals to L plus S is nothing but total angular momentum you are going to be call here. Okay. So actually, this is how we are going to get. Suppose this 2-electron system is nothing but for a hydrogen, we will be having only 1 electron you are going to be have. So similarly, suppose if you want to study about the 2-electron system, an example if you study, so we'll be moving for a helium if you take. Okay, helium if you take. So helium is an example which is having the 2-electron system, helium atom. Okay. So helium atom if you take, so this helium atom is having what? 2-electron system. It is a 2-electron system we have in the helium atom. Suppose if you consider this 2-electron system as an example of helium if you take. So in the case of this helium, actually we are going to get what we call different quantum numbers, which is having the spins. So actually quantum numbers which are associated, we'll see here. So we have a spin S is equals to 1 we are going to be have. S is equals to 1 because it is a 2-electron system. Spin will be 1, either 1 or 0 you may be having. Suppose if you take a spin S is equals to 1, you'll be getting what we call a triplet state you are going to be get. Triplet state. Since the 2-electron spins are parallel. So spins parallel ఉన్నప్పుడు అంటే parallel to the field if you are there. So half plus half. So half plus half is nothing but 1 you are going to get. So that is the reason why we have taken S is equals to 1 we have taken. And similarly, this is about the spin for a two electron system. And if you take the orbital angular momentum is nothing but what? L we have. So L if you take, so for it is going to be have what we call a 2p configuration. It is going to be have 2p configuration. Okay. So example L is equals to 1 తీసుకుంటే మనకి 2p configuration. Already we have seen in the case of the vector atom model. So for L is equals to 0, S electron. For L is equals to 1, we have seen P electron like that. So for L is equals to 1 here. So for L is equals to 1, what we are going to be have 2p configuration, it is going to be have 2p configuration. So therefore, S we know that 1, L is equals to 1, it is a 2p configuration. So therefore, J is equals to what we have? L plus S kada. J is equals to L plus S. So here J is equals to L plus S is nothing but how much you are going to get? 1 plus 1 you are going to get. 2 you are going to get. Suppose S is equals to 1, L is equals to 1 తీసుకున్నాం అనుకోండి. You are going to get 1 plus 1, 2 you are going to get. That is nothing but actually either it can take the J values as J, it can take the values like what we call 0, 1 and 2 it is going to be take. 0, 1 and 2 it is going to be take. J, it can take all these three values. So for J is equals to 0, we can calculate. For J is equals to 1, we can calculate. And for J is equals to 2 also we can calculate. So what is the value of G we have written here? In the formula, G is equals to what we have? 1 plus J into J plus 1 plus S into S plus 1 minus L into L plus 1 divided by what we have? 2J into J plus 1 we have. Okay. So therefore, if you substitute this value here, for J is equals to 0 initial case, for J is equals to 0 here, if you substitute G value, Landis G factor, you are going to get it as 1 plus. So J value is how much we have? 0, right? 0. So it will be 0 into 0 plus 1 plus 1 into spin is how much? 1 gada. 1 into 1 plus 1 minus L value is 1 again, 1 plus 1 divided by this 2J. 2 into J value is 0 into 0 plus 1 you are going to get. So that is nothing but how much you will get? The entire value, it is going to be 0. Something by infinite, it is going to be it as 0. G value, you are going to get it as what? 1 you are going to get. So like this, you can calculate for J is equals to 1. Also you can calculate, and for J is equals to 2 also you can calculate Landis G factor for 2 electron system here. So that is nothing but actually, if you see from the formula also, this Landis G factor. So what actually we have got? 1 plus this J into J plus 1, this entire thing we have got, right? So that is also we have written it as 1 plus J square plus S square minus L square by 2J square we have written. This one. This J is equals to this same, we are going to get it as 1 plus J square plus S square minus L square by 2J square we have got. So therefore, Landis G factor, it depends upon the what? Quantum numbers L, S and J. Because what we have here, okay, one more Alex. So the Landis G factor, we have got it as G is equals to 1 plus J square plus S square minus L square by 2J square. Otherwise, we can write that also. What we call what we call L into L plus 1. 1 plus J into J plus 1 plus S into S plus 1 minus L into L plus 1 by 2J into J plus 1. Both are same. So that is nothing but this Landis G factor is depending upon all the quantum numbers. What are the quantum numbers is this L, S and J we have. All the quantum numbers. L is nothing but what actually due to the orbital motion, orbital quantum number whichever we have. S is nothing but spin quantum number, and J is nothing but total quantum number by adding these two. So Landau G factor G, it depends upon the quantum numbers L, S, and as well as the J. And similarly, for a two electron system in this LS coupling, we have the formula like G is equals to 1 plus J, J into J plus 1 plus S into S plus 1 minus L into L plus 1 divided by 2J into J plus 1. Otherwise, we have like a G is equals to 1 plus J square plus S square minus L square by 2J square. Okay. So actually the G value, it determines what actually determines the splitting of energy levels in a magnetic field. So what we have studied, this uh, LS coupling in G factor is nothing but when we taken this two electron system into a magnetic field, two electron into a magnetic field. So we have studied that Zeeman effect. What is Zeeman effect? That is, suppose if you take an atom in the normal field, it will looks like that it is having some structure. But when we taken this into a magnetic field, it will be going to be split into in different energy levels. The splitting of these levels into sub levels, which we are going to be call it as what Zeeman effect. So here we are studying about the Landau G factor is nothing but it is going to be see how the what we call the splitting of energy levels in a magnetic field is going to be takes place. So that is what we call it as Zeeman effect. We are going to be called. Okay. So this is the Landau G factor for LS coupling. Okay. So similarly, we'll see the Landau G factor for JJ coupling. Next, we'll see this Landau G factor, Landau G factor for JJ coupling. Okay. So in the JJ coupling, as it is given that S and L of each electron are coupled. Okay, S and L. Okay. S and L of each electron are coupled together and quantized to form their own resultant J. Means either S individually or L individually, they are quantized to form their resultant J. It is going to be formed, right? So here the magnetic moments of the two electrons. So previously in the case of the LS coupling, we have written that mu L we have written, mu S we have written. But here it is individual electron which it is going to be coupled. So that is the reason why we will write the what we call magnetic couple of the two electron systems separately. Like for one electron, if you take, so for one electron, for the first electron mu1, if I write, so what it is given? G J1, okay, G1. That means for that particular electron, G1 J1 into He by 4 pi mc. That is magnetic moment of that particular electron. Similarly, if you take another electron, so for that electron, mu2, if you have, so then we can write G2 J2 into He by 4 pi mc we can write. Okay, He by 4 pi mc. Hmm? We have written mu1, that is the magnetic moment of individual electron, and similarly mu2, a magnetic moment of the other electron we have written. So here J1 and J2, we are going to be get by coupling together. Okay. So that mu J we will write here. Mu J is nothing but by combining these two. Mu J you are going to get. So mu J is going to be get it as what? First, for first electron, what we have? G1, J1, He by 4 pi mc. Okay. And here, we have what we have here. Consider the two electron system we have been considered. So what we have to do is we have to add these two to give the total magnetic momentum of the atom. So in the atom, we have the two electrons here. So that we'll get this mu j is equals to G1J1 into He by 4 pi mc cos of J1 and J. I'm not. So similarly for the second electron, okay, for the second electron, what we have? G2, J2, and we have He by 4 pi mc and cos of for that electron J2 and capital J. Okay, so this we have. So by combining these two, what we'll get is, so we have G1, J1 into this cosine angle between J1 and J plus G2, J2 and cosine angle in between them, J2 and J. And this we can take outside. That is what we have, He by 4 pi mc. So this is what we have the total magnetic momentum of the atom. We have taken for one electron as G1, J1, this entire value we have taken. And similarly, for the second electron, we have taken G2, J2, He by 4 pi mc into cos of J2, J we have taken. So by combining these two, we have got this total magnetic momentum of the atom we have got. Okay. So now what we'll do is we will replace this entire term, this one, whichever we have in the brackets, G times J we'll replace. So that is, we'll write it as G times capital J. So which will be equals to actually this entire value, that is G1, J1 cosine angle J1J plus what we have, G2, J2 cos of J2J. Okay, this one we are writing it as what? G times J we are writing. Okay. So then what we'll get, mu J is equals to, actually we'll get it as what again? G times J into He by 4 pi mc here we go. Okay. So what we have here is, not here. So as we know that the angles between J1, J2 and J are constant. So the cosine formulas are given by what? It is given that J1 cosine of J1J, which you are going to get it as what? Sorry, small j. J square plus J1 square minus J2 square divided by 2J you are going to get. Similarly, for second electron, J2 cos of J2J is equals to, you'll get it as what? J square plus J2 square minus J1 square by 2J you are going to get. Okay. So therefore, if you want the G value, so G value will be combination of these two. It is given G is equals to, what is that? It is given G1 J star square equation 11.4 it is given. So GJ formula we can write, that is land as G factor. So actually we'll get that as G, we are going to get it as, for first electron, it is what we have written, J1 we have written, right? J1 into J into J plus 1, okay, plus for that electron, J1 into J1 plus 1 minus, similarly, second electron you are going to be half, no? So that you are going to get it as what? J2 into J2 plus 1 plus G J2 you'll get divided by 2J into J plus 1. So whatever we have got that equation, G is equals to G1 into J square plus J1 square minus J2 square. So if you multiply these all, you are going to get the same thing. One, what we can have is like a J1, J2 are there, right? So what are those J1, J2 is nothing but J1, J2 are the actually the total angular momentum of the individual electron. Individual electron. That means J1 if you take, okay, J1 if you take, this is the total angular momentum of the first electron. So J2 if you take, so that is the total angular momentum of the second electron you are going to be have. Like if you take the capital J, combination of what? J1, J2 you are going to be have. That J is nothing but the total angular momentum of the system. Total angular momentum of the system. We are studying about what? Two electron system we are studying. So for each electron, if you take, so J1 you are going to get. J1 is nothing but it is the angular momentum of the first electron. J2 is nothing but what? Angular momentum of the second electron. Capital J is nothing but the total angular momentum of the system. Total angular momentum of the system. That means the combination of all the electrons, J1 and J2, we are going to be get here. So this is how we can what we call calculate this what we call JJ coupling in for two electron system. Similarly, as we have seen that two electron system, so you may be having like a what we call L1 values. Suppose if you take any example for a two electron system, if you take example L1, you may be having some value like a 1 you may be taken, and also S1. S1 is nothing but spin. It may be always half you are going to be have. So in this case, J1 you may be getting it as what? Either 1 by 2 you may be getting or 3 by 2. You'll be getting two cases. J is nothing but what? Combination of these two. Either spin, suppose if you have taken plus half తీసుకున్నాం అనుకోండి, so you'll be getting 1 plus half, it will be 3 by 2. Suppose spin if you have taken minus half, if you have been taken 1 minus half, it is going to be get 1 by 2. So therefore either you may be getting this as 1 by 2 or 3 by 2 you are going to get. This is for L value is equals to how much? 1 if you take. Suppose if you take like what we call L2 is L1 value, if you take 2 if you take. L1 is equals to 2 if you take. And the spin, always we know that it may be having half. So in this case, what you are going to get? Either you'll be getting 2 plus half. One case you are going to get. 2 plus half is nothing but how much? It is 5 by 2 you are going to get. Otherwise, what you are going to get? Another one? 2 minus half. So it will be how much? Sorry, 3 by 2 you are going to get. So for L, depending upon the L value, you may be getting. So similarly, you can get the J value also. J is equals to half if you are having J is equals to 3 by 2. Okay. Manaki J is equals to half okati vachindi or 3 by 2 vachindi kada in the previous case lo. In this case, we have got J is equals to like 3 by 2 we have got or 5 by 2 we have got. Suppose if you take in the case J1 is equals to how much we have got? 1 by 2 we have got. In the case of J2, suppose if you take 3 by 2. So total J is equals to how much? It will be 1 by 2 plus 3 by 2. It should be 2E. 1 by 2 plus 3 by 2. It should be 2 you are going to be have. So like that, we can calculate all the values of what we call J values and G values. And also these values, if you substitute in this equation, G is equals to what we have. Equation is 1 plus actually you'll get 1 plus what we call J into J. This one, G is equals to individually, if you write this, you are going to get it as a 1 plus you are going to get. Okay, 1 plus these values. So in this, if you substitute, you can calculate the values. Okay, GJ values you can calculate. For a 2 electron system, for particularly some example, if you take, you can calculate these all. Okay, so this is about the 2 electron system, JJ coupling you have. Right. For n is equals to 4, as we told that n minus 1 you are going to be have. N minus 1 is nothing but maximum value is 3. Like 0, 1, 2, 3 you are going to be get. So for L is equals to 0, S configuration, S electrons you are going to get. For L is equals to 1, P electrons. For L is equals to 2, SPD. Tarata F electron you are going to get. So like so this is what we have, what we call JJ coupling for Landis G factor. Suppose if you see what we call JJ coupling for G factor, what we call Landis G factor in JJ coupling. So G factor, it is going to be depends mainly on the what? G values. Here if you see, it mainly depends upon what? G factor depends upon what? The electrons. Okay, the electrons as well as the total angular momentum. Total angular momentum, it is going to be vary, as we have seen the example like J1 value is equals 1 by 2 or 3 by 2. If you are having J, you are going to get it as a 2. So it mainly, the Landis G factor depends upon the individual G factors. Okay, individual G factor of the electrons, like a first electron or second electron, whatever we are going to be have. And this formula G value in JJ coupling is more complex than in LS coupling. LS coupling lo manaki evostundi, in the case of the LS coupling, simply you will get like L into L plus 1 plus S into S plus 1 minus what we are going to get. We have seen the formula, no? In LS coupling lo, so the formula whichever we have got is L into this C. G is equals to what we have got there. J in 1 plus J into J plus 1 plus S into S plus 1 minus L into L plus 1. Here it is written that like a J square plus S square minus L square. by 2j వచ్చింది కదా. So there simply it is not complex. Simply it depends upon the J, S value and L value. Whereas in the case of this what we call JJ coupling, it is more complicated, like means than the LS coupling. Okay, the formula in G for G in JJ coupling is more complex than the LS coupling. In the case of the LS coupling, simply you have the J value, S value, L value, you can substitute. So here it is more complicated than that you have. Okay. And the value of G determines what we call Zeeman splittings. Okay, Zeeman splitting in a magnetic field for JJ coupling. So for LS coupling, Zeeman splitting for LS coupling we have. So in the case of this JJ coupling, the Zeeman splittings in a magnetic field. That means when we take this atom into a magnetic field, we said that it is going to be split into sublevels. So in LS coupling, how it is going to be split in the case of the magnetic field, and here in the case of the JJ coupling in a magnetic field, how it is going to be split, it will given. So next we'll move to what we call this. So we'll see this Zeeman effect. Zeeman effect for two electron system. Two electron system. Right. So generally we know that what is Zeeman effect? Just we studied that Zeeman effect is nothing but splitting of atomic energy levels in the presence of external magnetic field. So if you take the atom into external magnetic field, it is going to be split atomic energy levels. We'll be calling it as what? Zeeman effect we have been called. So that is if you take for two electron system, like example for two electron system is helium atom. Okay. So if you take a helium atom or with two electrons, two valence electrons, it is going to be have. So the Zeeman effect in the case of the two electron system is more complex than what we call single electron system. Why? Because the interaction between the electrons it should have and the interaction between the magnetic field, electron and magnetic field interaction, it should be there. So that is the reason why it is more what we call complicate in the case of the two electron system. So again, what we have to take here, it is we have to calculate the angular momentum J we have to calculate. So in two electron system. So in a two electron system, the total angular momentum is nothing but what? The vector sum of individual angular momentum of the electrons. Total angular momentum is nothing but what? It is a vector sum of the individual angular momentum. Individual angular momentum of the electrons. L and S. So that is the reason why what we have written J is equals to L plus S we know. J is equals to L plus we have. And similarly, we have the magnetic moment also. Because it is in a magnetic field, it is present. So we have the magnetic moment. So magnetic moment generally we represented with what? Mu we have represented. So mu is proportional to the total angular momentum, J. Okay. So mu generally we have written like a, what is that? G, J into mu J we have written. Okay. This is what we have the what we call magnetic moment, whichever we have. And Zeeman splitting is nothing but again, it is going to be split into different levels. It is going to be split here. Okay. So here we'll calculate this what we call value G value. We'll calculate for a two electron system here. So if you take what we call a weak magnetic field, the atoms of a hole quantized with field B here. ఇక్కడ H అని రాసింది మీకు. B also we can take here. Okay. So the projection of the angular momentum, it is given by what? J into H by 2 pi. J into H by 2 pi. As previously, we have written like what we call to H by 2 pi is nothing but what? That total angular momentum. Okay, J. Now what we have is the magnetic field is so weak. Okay, the magnetic field is so weak. So you are going to get this what we call first one is what we have here. It is first one. What we have is as the magnetic field is weak. First, you are going to get S1 and S2 precise rapidly around their resultant S. Means it will rotate slowly around the S you are going to be have. Similarly, this S1, S2 is nothing but spin. Right. Similarly, we have L1 and L2. Right. Similarly, we have L1 and L2. So this L1, L2 precise rapidly around the resultant L. Again, this it is going to be revolve around this, means a spin. It will rotate around this L you are going to be have. And the combination of this, L and S. Okay. The combination of this is nothing but what? L and S. So L is nothing but combination of L1, L2 you have. S is nothing but combination of S1 and S2 have. So this L and S, it is going to be precise around what? J. It is going to be precise around J in the direction of the field you are going to be have. Okay. So if you compare this, J will precise still more slowly around the magnetic field H. Okay. So now what it is given is uh, according to this what we call a classical model. Seen about Larmor precision. What is Larmor precision? We have seen. Okay. So that is given by as it is moving around that, it is going to be have the angular velocity, right? Right. So it is going to be have right. So it is going to be have what? Angular velocity. So that angular velocity it is given by what? Omega L. So omega L it is written as right. So omega L it is written as what? H into the field into G into E by 2 mc. So this already we have seen when we have studied about the Larmor precision. Okay. So now the precision J will change the total energy of the system. Okay. The change in energy is given by what? Delta E. The change in energy is given by what? Delta E. So which is a combination of this omega L Hg into E by 2 mc into this J into H by 2 pi into the angle between them, that is cos of JH, whichever way. Okay. Right. So that if you rewrite this equation, So what you'll get, delta E is equals to what we are getting here? Delta E is equals to G into, so EH by 4 pi MC we can write. EH by 4 pi MC into H into mu J. Okay. Mu J is nothing but what actually? That is the total magnetic momentum. Total magnetic momentum. Magnetic momentum due to the what we call spin and as well as this L. So that is a mu J we are going to get. So G into EH by 4 pi MC into H into mu J you are going to get. So here it is written, we can write this mu J. What is mu J? Mu J is nothing but what actually it is a J into cos of angle between them, J and H. This is nothing but total magnetic quantum number. It is a total magnetic quantum number. So now if you divide this with Hc, the energy in wave number it is given. So in terms of wave number we can get. So in terms of wave number, what we are going to get is right. So in terms of wave number, we are going to get that is delta Tm we are going to get. Okay. Minus n, we just will what we call, we'll take the magnitude as a delta Tm we are going to take. So which it is going to get it as what? M J into G into EH by 4 pi MC square you are going to get in terms of what we call wave number. So which it is written as what? Mj into G EH by 4 pi MC square, it is given as what? L it has been given. Okay, which is Lorentz unit. L is equals to actually in place of EH by 4 pi MC square, it is written. Okay. So దాని తర్వాత TM ఏం తీసుకున్నాం మనం? TM we'll get it as what? TM we are going to get it as T minus. So that is nothing but delta T is nothing but is equals to T minus MJ, sorry, MJ kada adi, minus MJ into GL you are going to get. So this one. Okay. So this is what we have, what we call splitting of this, what we call this energy levels when we keep in a magnetic field. So for two electron system. So for two electron system, they have taken one example like MJ values, which is going to be take values of how much? 7. Okay. The values of this, it has been taken from 0 to 1, 2, 3, you have 0, -1, -2, -3 you have. Okay. So if you substitute all these values you are going to get all these like a 12 by 3, 8 by 3. In this, if you substitute 1 plus j square plus s square minus l square by 2j square. In this case, if you substitute like g is equals to what we have 1 plus j square plus s square minus l square by 2j square. Okay. So in this case, if you substitute all the values like mj values, whichever it is going to be taken, mj values like starting from 0 to 3 and 0 to -3. That is nothing but 3, 2, 1, 0, -1, -2, and -3, whichever it is going to be. So these, if you substitute, you are going to get like 7 different values of you are going to get. So that is 12 by 3, 8 by 3, all you are going to get. Okay, 12 by 3 and 8 by 3, 4 by 3, 0 ki 0 వస్తుంది. Then you'll get minus signs, -4 by 3, -8 by 3, and -12 by 3. So that spectral representation, it is given here. Okay. Then spectral notation ఇక్కడ ఇచ్చారు చూడండి. Like for another example they have given. What is that example we have here? It is what is that? The transition between 1D2 to 1P1. Okay, 1D2 to 1P1. So for 1D2 to 1P1, you'll have like a S is equals to 0. S is equals to 0 వస్తుంది మళ్ళీ and we have G is equals to 1. Okay. So in this case, what will happen means J will be splitting into 5 different sublevels. Our 5 different sublevels వచ్చేసి like you'll have like a 0, 1, 2, 0, minus 1, 2. Okay. This is 0, 1, 2, 5 different levels. You have -1 and -2. So for S is equals to 0 and G is equals to 1, the initial level with J is equals to 2 will split into 5 sublevels. And when J is equals to 1, 3 sublevels. For J is equals to 1, 3 sublevels you have. So 3 sublevels and automatically you have like 0, 1, -1. So it is 0 ఉంటుంది. You have one -1, another one is a +1. So this is for 1P1. So for 1P1, this J is equals to what we call 1 we have. ఈ నోటేషన్ తెలవాలి మీకు. This notation 1P1 notation, what is 1, what is P, what is 1. So for 1D2, 1D2. For D అంటే ఏదొస్తుంది మనకి? L is equals to 0 means S electron. L is equals to 1 means P electron. L is equals to 2 means D you'll get. P means L is equals to 1 you'll get. So for that one, what is the S you have? S ఎంత ఉంటుంది? హాఫ్ ఉంటుంది కదా, -half ఉంటుంది. రైట్, L plus S వస్తుంది. L plus S నథింగ్ బట్ సపోజ్ P అంటే ఏంది? 1 కదా, L is equals to 1. L is equals to 1 ఉంటుంది, S is equals to హాఫ్ ఉంటుంది, -half ఉంటుంది. So like that 3 different levels you'll get. So వాటి మధ్యలో transitions you'll get these different transitions you are going to get. So this is how you'll Which between LS and JJ coupling schemes for two electron system with vector diagrams. This is not a G. What we call in the case of the Zeeman, Paschenbach, and Stark effect, you'll get a one long question. Unit 9 very important. That is you'll get Zeeman, Paschenbach in the other Unit 9 low. So Unit 9 low, you have this what we call Zeeman effect property. You go to Paschenbach effect and Stark effect. So you'll get a compulsory question from that one. Zeeman, Paschenbach, and Stark effects. So you go through compulsorily this Unit 9, complete Unit 9, and Unit 10. Unit 9 and Unit the vector atom model, you may getting long question, and as well as what we call this Zeeman effect or Stark effect, any one of them. Zeeman effect already I have told for experimental arrangement and all those things. So that these two block units are very important in this block. Atomic spectra. మీకు ఆఫ్టర్నూన్ ఉందా క్లాస్ ఉందా?